Let's take a look at example 2. We want to use a triple integral to find the volume of the ellipsoid given by 4x squared plus 4y squared plus z squared equals to 16. We've graphed and dealt with these kind of objects earlier in the class. The first thing we would want to do is begin by solving this function for one of the variables to get some bounds. Doesn't matter, they're all kind of symmetric in the sense that there's not one convention that's going to make it easier than the others. But certainly it might be a little bit easier just to get the z by itself, because then we don't have to clear off any extra coefficients, and then that would give us z bounded between x and y, a function of x and y. So let's go ahead and do that. So we have the function 4x squared plus 4y squared plus z squared equals to 16. We want to get the z by itself. Z squared would be equal to 16 minus 4x squared minus 4y squared, and then just simply take the square root of both sides, and we get that z is going to be equal to the square root of 16 minus 4x squared minus 4y squared. With this particular ellipsoid, one of the things that we know is that it has some symmetry. So instead of having to work with the entire figure, what we might want to do is let's just work on a portion of it. So I'm only going to draw the portion of this in the first octant, and then what we can do is just multiply the triple integral we're going to set up by 8. So if we think about this ellipsoid, this is just one little piece of it. This would be an eighth of the total region. Here's x, here's y, here's our z-axis. So if we're going to focus on it within the first octant, then z itself is going to be bounded by this function of x, this 16 minus 4x squared minus 4y squared, and because we're looking at the first octant, it's going to be the part above the x and the y-axis. It's also bounded between 0 and z. Let's now take a look at y. So we want to come up with some bounds in terms of the expression for y. If we look at y in the xy plane, the relationship would be that 4x squared plus 4y squared would be equal to 16. We can go ahead and subtract 4x squared from both sides. We can divide by 4 and then take the square root, and we would see that y is going to be less than or equal to the square root of 4 minus x squared, and it's also in the first octant, so y is greater than 0. So these would be the bounds for y. And then if we look at x is going to go from 0 to 0 to 2. On the x-axis, if we have 4x squared equals to 16, x squared would be equal to 4, so x would be 2. So x is going to be between 0 and 2. Now that we know this, we should be able to set up our volume integral. So we know that the volume is related to the triple integral over the region dv. This is going to be 8 times, because we're doing just the first octant in terms of our bounds, from Symmetry, if we just multiply this triple integral by 8, it'll give it to us. We chose to do the order dz, dy, dx. Our bounds for z are going to be from 0 to the square root of 16 minus 4x squared minus 4y squared. Our bounds for y are going to go from 0 to the square root of 4 minus x squared, and our bounds for x are going to go from 0 to 2. Alright, let's start to integrate. We integrate with respect to z first. We're going to have 8 times the integral from 0 to 2, the integral from 0 to the square root of 4 minus x squared. The antiderivative of 1 dz is simply z, and this gets evaluated from 0 to the square root of 16 minus 4x squared minus 4y squared dy dz. Evaluate the antiderivative at the upper limit of integration, subtract it, evaluate the lower limit of integration, and we get that this is equal to 8 times the definite integral from 0 to 2, from 0 to the square root of 4 minus x squared. We plug this upper bound in for z, we get the square root of 16 minus 4x squared minus 4y squared. If we plug in the 0 for z, that's going to be subtracting 0. So we're just going to leave that part off. And then it's going to be done dy dx. So the next part is we're going to have to integrate this expression here. Okay. So we need to find the antiderivative of this thing in terms of y. Well, in order to do that, let's kind of simplify the integrand a little bit. So let's do the following thing. We can rewrite this. First of all, I have the square root of, there's a common factor of 4 we can pull out. This will leave us with 4 minus x squared minus y squared. The square root of 4 is 2, so we get 2 square roots of 4 minus x squared minus y squared. And now we're trying to do the antiderivative of this with respect to y. This is one where if you try to look up this, try to do this, it's going to be a little bit involved. But we can actually use the use of an integration table to kind of help us out on this one. So if you use integration by tables, it's going to look in the following form. So you go to the back of the textbook, you'd be looking for something of the form like a minus y squared. In the book, it'd probably be a minus x squared. But we should get the following antiderivative for this piece. This is going to be equal to 8 times the definite integral from 0 to 2. From our integration tables, we get that the antiderivative with respect to y is going to be y times the square root of 4 minus x squared minus y squared plus 4 minus x squared x squared times the arc sine of y divided by the square root of 4 minus x squared. And this will be evaluated from 0 to the square root of 4 minus x squared dx. And if you're looking for a reference for that formula, this is going to be Appendix B, and it's going to be formula 37 from our integration tables. So that's our antiderivative in the variable y. We are now going to evaluate this function at y, at the bounds. So everywhere I see a y into this expression, I'm first going to put my upper bound. This is equal to 8 times the definite integral from 0 to 2. This is going to be the square root of 4 minus x squared times the square root of 4 minus x squared minus the square root of 4 minus x squared squared plus 4 minus x squared times the arc sine of the square root of 4 minus x squared over 4 minus x squared dx. If I substitute in the lower limit of integration, if I plug this in for y, just be very careful. If y is 0, then this whole term would be 0. And then plus, if I plug 0 into the arc sine of this thing, the arc sine of 0 is indeed 0. So the entire antiderivative evaluated at the lower limit would be equal to 0. So I have this with the antiderivative evaluated at the upper limit. The lower limit just gives the value of 0. And so this is what we're left with right now. Okay. On the inside of this piece here, if we look at what we have here for a moment, this is the square root of 4 minus x squared. This square root and this square cancel, so we end up subtracting 4 minus x squared, and that becomes just the square root of 0. So this piece will drop out. That's going to be equal to 0, leaving us with 8 times the definite integral from 0 to 2. Now over here, this is the same thing divided by itself, so that's 1, and the arc sine of 1 is going to be equal to pi over 2. So we end up just getting a constant, pi over 2 times 4 minus x squared dx. And this is not bad at all. I can bring the pi over 2 out. 8 times pi over 2 would give us 4 pi times the definite integral from 0 to 2 of 4 minus x squared dx. It's about as elementary as an antiderivative as we're going to see these days. We can certainly work this out. This is going to be 4 pi times the antiderivative of 4 minus x squared with respect to x is 4x minus x cubed over 3 evaluated from 0 to 2. This is going to be equal to 4 pi times 8 minus 8 thirds minus, this will be 0 minus 0. So we get 4 pi times 8 minus 8 thirds, which with a little bit of arithmetic will work out to be 64 pi over 3. So the volume of that sphere works out to be 64 pi over 3.